Okay, good afternoon, everyone. Let's get started for our fourth lecture on polymer configuration. So it has been a very nice and exciting journey for the past few lectures. We started a very simple model from free joint chain and to a little bit more sophisticated model to free rotation chain, and some of the more fancy one is hindered rotation model. So today we're going to talk a little bit more about something even one step further into the chain configuration. Okay. For the last three chain model we discussed, all of the polymer basically has a single bond, and the bond basically free rotates. What if in real life you have something not that easily rotate, and how do you treat the model for those type of chains? For example, there is a classical example people like to give regarding these chains. They call it semi-rigid chain. Okay, so let me give you an example. Think about your own big garden, and you need to water your garden constantly, and you probably need a very nice garden hose. And they sell two types of garden hose. One is sort of more robust. They sold as very rigid. It has very thick walls in these, so they tend to be very long-lasting because they have very thick wall. Well, it's perfect for me because I like something can last forever, but my wife don't like that. She likes something that very thin, very light. You know, something that sell online is expandable, so they have the elastomer in it and super light. Once you turn the water hose on, it's getting expanded, right? So the point is, if you think about that, the hose I like to use is fairly rigid. If you think about size scale, about several inches long. So within a section of this, it's almost very hard to bend that garden hose. So that's why it's kind of a pain if you want to walk long distance and carry a very long hose with you. But if you buy the hoses, it typically comes with a very long, right? It's something around 20 or 50 feet. In that length scale, actually it's fairly flexible, or they can even coil it up. That's how you, at the end of the garden work day, you basically roll them up to be a large coil, right? So my point is, every chain rigidity is relative. It depends on the size scale you look at. So on the very tiny scale, it could be very rigid, but on the larger scale, it will be relatively soft. Coming back to the topic we talked about a couple of days, we talked about end-to-end distance, h, right? So this is a parameter that people used a lot. And the second parameter we talked about last class is characteristic ratio, or called C infinity. And I mentioned a little bit about the difference between these two. This one is overall dimension of your material. And unfortunately, H does not contain the information about how rigid or soft your material is. H only tells you how big your polymer is. Right? There's no embedded information about my polymer is soft or my polymer is rigid. There's no information. I can give you an example. If you have a rod-like polymer, you can have it straight, about this big. But you can also have a flexible polymer occupy the same roughly end-to-end distance, but they didn't tell you how rigid that is. The second parameter, characteristic ratio, is much better term once you describe how rigid your material is. And we didn't talk too much about how that translates directly to how rigid a material is, but today we're going to talk about another term that will be directly linked to this characteristic ratio. So by the middle of the class, hopefully, after 40 minutes, we will learn about everything about this persistence length. This is a new term that we will talk about today. So a new term. These two are interrelated. They both used to describe chain rigidity. Actually, not even after this class, you will learn they have a simple relationship between these two terms, and I'll explain. So let's get started to talk about this new term, persistence length. Anyone can give me a clue what is, if you look at the dictionary, what does persistence length would roughly tell you? How persist this person is? Huh?
A measure of not wanting to change, I guess?
Yes, perfect.
If you take a point on that curvy chain and you set almost like a tangent line to that point, how long it stays along a single path.
Yeah, that's very good physical term. At the beginning, let's just think about a little bit more abstract. Persistence is how something refuses to change, right? It is, but I will talk about the way you described how scientifically this is described as persistence. But by definition of dictionary, I actually like this physical term because this is some physical meaning you can guess from what it is called. So persistence, you can think about, if you really like something, you want to put all your attention to it without being distracted. So you're called very persistent. Similarly, for a chain, persistence length is talking about how this chain, at the beginning of let's say you have first the segment of your bond, right? We always call it L1, and you are going to have the second L2. So persistence length is just to talk about how this chain is persistently trying to follow the previous bond angle, okay? So the direct way you can understand is high persistence length means this chain is fairly refused to change. So if he wants to go to the south, he will always travel to the south, okay? No way he wants to turn around or do something else. So if we know LP goes up, your chain is more rigid. So that's how people come up this term to describe how your material is. Now, before I start to talk about more details way about the equations and how we understand the relationship between these two, I want to ask you, what would you guess the persistence length for two extremes? One is a super soft chain. Let's say extreme is free rotation chain. What if this thing can move around freely? What would you think the persistence length for this? Right? Case 1, free rotation chain. LP will be short, right? So it will be very, very short. It won't be taking too long. And I'll jump to case 3. And this is a hint. There's going to be something in between. How about this case? There's no chain model, but it's called a rigid rod. So what would you think the LP would likely to be? It will be very long and could be also be infinity, right? Long or infinity. So since we already talked about the last class several times, I can tell you this will be longer than contour length. Contour length is sort of the longest length for a polymer chain, right? If you have L and L, which is, well, you pull the chain straight, so this will be longer than NL. Okay, so whoever came up with this term is a great guy. Very easy to understand, persistence length. If it's longer than, let me also put one more term here, okay? So LP will be equal to one segment is for free joint chain. And we will show you why that's the case. Basically, it's only persist around one chain bond. All right. So there must be something in between. That's where the most of the polymer are in real world. So we will talk about this in this class. And at the end of class, we will learn what would be the persistence length for these polymers you are familiar with, polystyrene or polyethylene, etc. Okay? Where shall I start? So is there any terms we learned in the last few classes? How do we consider if the chain is following the previous chain's direction? We sort of talked about one operation can do that trick.
It utilizes the angle of one bond in relation to the other, right?
Right,
okay.
Right, exactly. So what we can do is just relate how much angle band between the bond next bond to the previous one. And before I jumped into that, there's a direct way or very physical ways you can understand the persistence length is when does the chain, while you walk along the chain, it will do this way, right? A lot of things, then it will finally bend it over. So the persistence length has a very interesting physical meaning is when your bond is bend at 90 degrees. Okay, what the distance takes is to bend 90 degrees. So, for example, this takes this much bond to bend 90 degrees, then that's the definition of the persistence length. All right, I'm glad that I covered all the real-world meanings that will help you to bring you up to date about what I'm going to talk about next. So this will be the L1, L2. Then the persistence length is kind of easy. Well, something bending at 90 degrees, we know L1 dot to L2 will be L1, L2, and the angle theta between them, right? And if it's 90 degrees, cosine theta happens to be 0. If theta is 90, let's see, if theta equals to 90, so this will be 0, right? So now you can see a very simple way to do the mathematics understanding about this is just to use a dot product. You want to do the dot product of your chain, multiply by its initial direction, and see what the value comes out to be. That's your persistence length. So let's do it. So again, 3 lines means it's by definition, this persistence length will be your bond. Remember, that's how you write your chain, right? Or the chain H will be this thing will be equal to L1 plus L2, and there's no square there, so it's a vector, right? H is vector, just tell you how does these everything added together. And persistence length is just a dot to this direction. So all the other words is how does these follow this direction. So we can just do a very simple dot L1, which is the first bond direction. Is this part straightforward to you? What this dot pattern mean? However, if you very quickly you realize we actually multiply L1, it's also a component of its length, so we need to normalize it, take off the length, only leave the angle direction of that. So what we need to do is divide it by or let's write here, divide by L. L is now just a magnitude, or how long this individual bond is. Remember? Or L basically equals to magnitude of L1. So let's tell you what the unit length for each bond is. So this will tell you mathematically how does the persistence length for the given bond. Okay? And the meaning is basically you have a long chain, and this would be the original direction, how much projection you have left on there before it's banded, right? So if it's very long versus in the second case in this, then it's band 90 degree. This will have longer persistence than compared to the first one, right? So this you can just basically break it down to individual parts. So we know H is add-on of each individual segment. So you can basically take it apart and add a little by little projection together to get this large persistence length. Which I mean is basically you add this into L, and you can expand this equation to be. I'm going to move the L to the front. Then this will be L1 dot L1, L1 dot L2, L1 dot to the Ln, right? So this is telling you how individual bond has a projection in the first bond direction. I can slow down a bit. Let's see what this component is. This is basically the L1 project its own direction, right? L1 dot L2 is how much L2 components share the same direction as L1. And you got L3 all the way added up to Ln. That's basically, by definition, is what the persistence length is. A question?
Is that 1 over L or L over L?
1 over L.
Okay.
Let me write L in this way so you guys can see. So this is basically no longer a vector. There's no square on the top. So in this way, what we get is now we have a mathematical operation. You can understand what would be the persistence length from what the direction is, right? And we talked in the previous class, you know what this part is, right? L1 dot L1. It's called self-turn. The outcome will be, someone help me?
L squared.
Yes, that's L squared, right? So this will be L1. The first term is L squared plus, if it's free rotation chain, there's not going to be any correlation. So this will be the 0, right? So which will be, everything will be 0 for free rotation chain. And you can see for free rotation chain, your persistence length just going to be same as value of L. All right? Pretty straightforward, right? So persistence length is the dot projection of your vector on the first section of your bond. And we expanded this into multiple segments from L1 plus to Ln. Then we did another expansion, basically putting in this L1 to each component. That's where we got this term. And this is cell term is basically L squared. And for free rotation chain, everything else is basically going to be 0. And that's for free rotation chain. You will see the persistence length is just itself by one single bond. And physically, you can understand, as I said, the persistence length is how long it takes your chains to bend 90 degrees. If you have a free rotation chain, right? So the second bond can immediately bend 90 degrees or even further, so it will lose persistence at first bond angle. That's why persistence length will be equal to L. Okay? So is it clear for everyone? What would be the first case? For the most simple one, how does free joint to the chain has that part? Oh, my bad. While I'm speaking, I spotted an arrow. This should be free joint chain. Ooh, that's a pretty big, better one. Because now I'm going to start talking about free rotation chain. Because when you have a fixed angle, now things getting a little bit more complicated. Because then, when does it take for the bond to bend 90 degrees? Will be a little bit more challenging to speculate, right? So now let's talk about the real one, free rotation chain. You're going to have a bond angle theta. Theta is fixed now, right? It can rotate around the stem, but this theta is fixed. Now you're going to have second one, which can rotate around the theta again. So this will be fixed, but this can rotate in plane, right? So you're now going to have something look like this crazy. But in this drawing, you can sort of guess it will probably take a few chains to rotate it to the 90 degree. But we're now going to figure out actually how big that is. How does that depend on the theta angle? Because you can see the bigger the theta angle, LP will drop, right? Because the bigger the theta angle between the neighbor bond, so this is the carbon, this is another carbon, the bigger it is, it's more likely to quickly pass the 90 degree bend angle. On the other extreme, if you fix theta is 0, you're going to have a super rigid chain that will have a super long persistence length, right? Your LP will close to infinity, just because you now get every bond is kind of straight in this case. All right, let's talk about intermediate. So for theta is an intermediate. How does LP equal to? That's a major part for the first part of the class. And this will help you to understand for a free rotation chain model how everything will become. And we can sort of guess it will be some value in between. It will not be all the way long, but not be all the way short. And I'll give you another hint. Those two are relative. They share blood many generations before, so they are somehow connected. And we will figure out how they are connected. Are they uncles, nieces, or anything else? All right, so without talking too much, I will jump into, again, coming back to this equation, we will see. This part is still going to be held in the equation that L dot by itself is still going to be L squared. And this now, we just cannot ignore now, right? This will be a value going to be persist there. And if you guys remember in the last class while we were talking about end-to-end distance, we also handled this problem. If it's not 0, how do we do that? We actually come up with a term called alpha equal to cosine theta, and we use that to simplify. But today I'm not going to go in through that route. There's another route we can take as a shortcut. And there's some magic we can play between this and end-to-end distance. Because in the end, your end goal is trying to understand how they correlate together. And if there's some way we can understand how does LP and link to end-to-end distance, then we can guess or directly combine them together. So how does that work out? So for this particular equation, we can basically rewrite in a sum term, right? So it will be equals to L 1 divided by L. Then you're going to be sum it up for L1, and let's call it Lj. J would be equal to 1 to n. It's basically summarize this term into this relatively simple equation, right? Now we're going to play a little bit because this somehow is sort of very close to what is end-to-end distance look like. If you everyone remember, end-to-end distance h squared is equal to for a general term. We don't need to know the value of that. So is it that would be the general term for what is end-to-end distance. Not considering what the model. It's model independent, right? So what I'm trying to show you guys is how we can convert this equation magically to this one. There's, it's halfway there. It's a little bit different, but we can walk around that to get it going. And this, I want to bring you a quick memory about what we played with. There was once a time we talked about there's self-turn and there's non-self-turn, right? There was such a matrix where everything on this diagonal is basically a vector dotted by itself, and everything not on the diagonally is non-self-turn. So what I'm trying to show you is now, for this particular line, it's basically the top row of your equation. Because, forget about this part. So this is L1 dot L1 plus L1 dot L2 plus all the way dot to Ln, right? So it's basically this row. And because of it's a vector term, what people found is this, you can do a little bit of math trick to make it a randomized matrix. Now it's a little bit tricky, so don't lost, follow me. L1, it will be equals to I not equal to J that would be the final results. Fairly close. Fairly close, but J not equal to I, but they're interchangeable. So how does this works out is now we can randomize this matrix. And what I'm going to do next is the textbooks basically mention that you can do a trick where you basically multiply by this by 2. If you multiply, let me make sure everyone follows on this part. So this is basically LP, right, on the far left. So this is what LP would be equal to. So if you multiply by this by 2 on each side, So you multiply by 2 on the left, and then you multiply by 2 on the right-hand side. You can rewrite this to be 2, 1 divided by L, I equals to 1 to n, and again j equals to 1 to n li dot lj. And during this counting, we're going to miss another L. Just because in this self term, if we count it twice, there will be one term along this line is missing. I sense a moment of silence. I guess, let me reiterate what we are doing here just one more time to bring you back. So what we're trying to do is to convert this equation to this equation. And the whole point we are doing this is you will soon realize this actually is a term that equals to h squared. So we are doing a fancy transformation of the matrix to combine what is LP and what's end-to-end distance. And all we are doing now is just to expand these terms to the matrix, and we're going to count the matrix twice to overcome what we did in the last class. In the first class, what we did is to take out this term and only count half of the matrix. What we are doing today is do backwards. So you're going to multiply this 2 to generate this matrix and count it again.
So what you just wrote on the board now equals 2LP?
Here?
Yes.
No. It's not directly is 2LP. So this on the left is 2LP.
Yes, so that whole function
yes.
on the right side.
Yes, this will be 2LP. You are right. So that's why we multiply by itself by twice. So what we will see, so in this term, in the center part, this is going to be directly related to NL squared, right? Because this is the end-to-end distance for your material. So this, let me show you. I will write this equation on the top. So this is L, and there's L squared. They can cancel out each other.
Will the 2 distribute through to the plus L?
Where?
Will the 2 distribute through to the plus L?
2 distribute to the plus L.
So like you have a 2 in front of 1 over P. Does that
Here.
mean that plus L is plus 2L?
No. This is only to the first term. So L is just by itself. L doesn't need to be multiplied by twice. L comes from the fact that while you count the matrix, because what we did is, we only have the half matrix. So we're going to magically give it a half from the bottom half. And that half is somehow using this mathematical equation that 2LP. So you 2 multiply by this, and you will generate 2 multiplied by here. There's this fancy term comes up because while we were counting this, we missed the 1L from the diagonal. I see there's still quite some confusion in the audience. Well, so let's continue to. So if anyone has specific confusions about this mathematical transformation, you can talk to me in the break during this. But for the sake of the continuation, what we're going to do next is to just continue to discuss how this LP will be linked to C infinity and L square, okay? So this, well, let me try again, explain this transformation from here to there. Because that seems where the most confusions is coming from, right? Because what we did in the first step is basically we considered this part. Is this equation sort of pretty straightforward for everyone? That's basically we're trying to rewrite this very lengthy equations to a term that everyone can understand. Correct?
So that term is just summing
everything together.
All of the extractions of the L chain, and when
right.
you sum all those up, you get
right.
persistence length.
Right.
Okay.
So how come you have the average? How come it's an average dot product rather than just like an absolute value?
Because while we talk about what I draw is like a bond, but in real world, so it's the bond can rotate. So we need to take a time averaged number. So that's why while we write the equation, we always kept this bracket term. That means we're going to average whatever all the possible orientation L and all the possible orientation L. And then we sum them together to get the final word. Let me actually explain again to everyone for this part, because we cannot move forward without clarifying this part. So what we had is, let me pull this part out. So this is LP would be equal to this is straightforward for everyone, right?
Where does the 1 over L term come from?
So 1L is because L1 has a certain value. So divide by L is just to normalize the length of that. Okay. So because we only wanted the directionality, we don't need the magnitude from L1.
So you're going from vector, so you don't want the magnitude, you want just the direction?
Right. So in LP, this is not a vector. LP is just a value. What we need is a value or distance, tell you how long you're projecting along the original length. And what we can do is, also you can know this. They call it a unit vector. A unit vector is basically a vector, only have the direction, but no magnitude. So you can think about unit vector basically going to be equal to vector L divided by L. So this is the length of the bond. Okay? So this is only give you the direction, but no magnitude.
What are the units on LP?
Unit, though, this is a distance, so whatever you got, it's angstrom nanometer. It's basically a physical length. Well, these are the vector where L1, Lj is telling you where the directions are. So L1 dot Lj, it just tell you how much Lj has a projection down to the L1, right? So if I explain one more time what is this, L1 dot by Lj will be equals to the magnitude of L1 and magnitude of Lj. Since these are the bond, they would be the same in cosine theta. So this will be L squared cosine theta, right? So that's what the dot product is.
And that is essentially just your distance in.
That's a distance.
The horizontal. We'll call it the horizontal direction if you're looking like at that chain.
Yeah.
Right up on the board.
But it's missing a value of L, because look at here. This is L squared cosine theta.
Yeah.
What's the direction product? Well, we mean we only need to know what is these values. So this value is L cosine theta, right?
Mm-hmm. Yeah.
So this bottom part. This is what we care about for this particular part. So if we normalize this by divide by 1 over L, this is what you're going to get. It's just the value of projection here. So now I'm going to divide everything by L1 squared multiplied by L1 Lj. Then this will become L cosine theta, or the projection here.
Yeah.
That's where this 1 over L is coming from, right? Because I only cares about the directionality. I don't need the magnitude from L1.
Yeah. Yep.
So that explains why we can write this part as a persistence length. So in other words, so now as I explained, what we do is now we get this, how long this term is. This is the length. This is not a vector, right? If we have another bond coming to the tail of it, it will point to a new direction. And this, if you consider this and first one, this guy will leave a little bit trace along the first bond, right? So that's basically a little bit here. That's again, this will be L cosine. This is going to be a new angle, but you got the point. It will keep going until this thing goes 90 degrees. Then this will not contributing any additional projection down here. So this term, the other way we write it is expanded term. Basically, these, the first term, second term, third term are these, little by little distance projection along the first vector.
Yeah. So LP is the distance in the x, not the distance or the length of the chain.
No. It's a distance, or it's basically the distance along the first bond. When does the chain start to bend over 90 degrees? So that's why, we started to talk about all these. I'm trying to explain in the physical meaning first before we jump into equation. So in other words, so if you look at this blue cable, down below, let me take this guy up to explain to you. So is it plugged in? It's plugged in. So let me take this part as an example. So now think about this starting point of your polymer chain. Well, it's going to the right, but it's bent to 90 degrees here. So persistence length would be from here to where my finger here. So this is going to be the persistence length of that. The length takes to bend 90 degrees, not this length, but in the bottom, this length. Okay? So coming back to this part, where I think we should take a break, then let everyone here take a little bit of mental break. Then I'll try again to explain that the fancy matrix theory, how they actually convert this to the one we talked about. Let's take a 5 minutes break. Now what the important is, I start talk the most simple one. So if you get a little bit confused about the fancy math, we talked a little bit later part. try to focus on the first part where we talk about the physical meaning at the beginning, what the persistence length and how they related to the bond bending, etc.
It does simplify into a simpler
Right.
version,
Right.
Okay.
Good. Okay, let's take a 5 minutes break, then I'll finish that part.
Are we going to go over where the next step where we multiplied 2 and then we got
Right.
the
Right.
double sum?
Yeah, I'll make sure everyone understand that before I
Okay.
move on, because
Okay,
that
cool.
is a little bit magic trick to everyone.
Yeah.
Yeah, physicists or mathematics like to play tricks so they can get to the end product what they want. But in the end, it's going to be simple, very straightforward
Okay.
connection between two.
Are we going to be responsible for how you drive these
No.
expressions? Okay.
But it would be
That's
good if we know why we get there in the
Yeah.
classroom. I think it will be valuable. I explain to you, but in a little bit more detail than the textbook does. The textbook gives a lot of useful information already.
Yeah.
But what most important when we talk about first 20, 30 minutes about physical meanings of how we quantify the chain rigidity using the concept of persistence length
Yeah.
and what persistence length is. Let me bring it. we're missing Nate. Let's give it a few more seconds, then we can resume for explaining.
So is that 1 over L, is that essentially just units? Is that like just a unit thing?
Yeah, L is
Has
just
no
a unit.
magnitude? Or does it have a
No, it has a magnitude.
Okay.
It's so what
L is that?
L is just how long the bond is. If it's just a 1.5 angstrom, it will be the value of that. So this is a magnitude, where this is vector.
Yeah.
So we basically, what we did for this unit vector is, this is no length, but it only has a direction.
Nice fire zone, some snow on the ground.
So this is direction only in this one.
Canceling the units out of that.
Right. So it's only left, because this one has two components. It has direction and magnitude, right? It has a direction of whatever it is, and it has magnitude of L. So if we divide by L,
Yeah,
it
so
will.
it'd be like 1.54 angstroms, but in any direction, or no direction, no specific direction.
Right.
So then you're just getting.
So the unit vector is just a 1, let's say, or just a unit. It doesn't have any length to it. It's only tell you where the angle is. Okay.
Do you usually like define like a set of axes or anything when you're?
Mm-hmm.
Do you define like axes when you're solving a problem like this?
So not really. So in this particular, we're using generalized model, so there's no direction to it.
Okay.
So let's continue to explain this fancy transformation. I think confused some of you, right? Well, I sense a silence. That's usually not a good sign. So let's try it again. We got plenty of time. So, and everyone is on the same page for this one, right? How we can get this one. So a question in the back?
Why do you have delta under L1 now?
No, I just trying to highlight it while we explain to other. No meanings, and there's no such thing as delta symbol. Okay. So coming back to this, what we can do is write again. What I'm trying to say is, what I mean the randomize, I guess I didn't explain too good, is randomize means this J equals to 1 can be any vector along your polymer. So it's not necessarily need to be all the chain projected to L1. Persistence length is unique to your chain. So it doesn't matter where I start to count it. That's the point. So if you start from L3, L4, 5, 6, whenever it becomes, turn 90 degree, it's the same as start from L1. So that what I mean randomize is basically that, meaning it will be equals to J equals to, let me make sure, X. X is just anything on any segment on the bond. So this will be any bond you pick you wish to calculate. Does not necessarily need to start from the first bond. But as long as it doesn't matter which bond you take. Let's say you take the one bond. If the persistence length is roughly 10 bond, after 10 bond it will bend 90 degree. If you take the third one, it will do the same. After 10 bond again, it will bend 90 degree. So no matter which one you pick, or what I mean randomization is J, as long as we start counting from the J equals to X and forward, so X can be any bond. So if we put L3, then count L3 forward, it's basically the same. You will get what LP is. Only difference is now we start counting from third bond. Okay? Now if you look at this matrix, is basically LP is now, if L equals to 1, this will be this part of the equation, right? 1 to forward. If you start counting X equals to 2, you're going to have this part of the matrix. Well, 2, 2, 2, 2, 3, 2, 4. While X equals to 4, you're going to start counting from 4, 5, projection from 4, 5, 4, 6, 4, 7, etc. And because this can be anything, or the word I used is randomize, you can basically count all the way to n. And what is become is basically saying, we are now counting all the metrics here. The top part, the top half triangle of what this thing is, using that randomized equation. For some reason, if we can add the bottom half, then we can use the end-to-end distance to describe this matrix. Right?
I thought we were just doing the top row for that.
Right. So that's a little bit of confusion part for this particular equation is after this transformation, now it became the half part of the matrix. If you look originally this was only the top part.
Yeah.
Now after this, that's what I mean, it's a little bit confusing, is now you're looking at the top triangle.
Okay.
It is indeed it's a little bit confusing to me as well.
Okay.
So what do we, please?
So is the important. So we just kind of like went on a mathematical journey to get to this last one is basically what we just did.
Yeah.
Okay, that sounds good.
Yes. Yes. So what I'm trying to explain is how in the book you are reading, how they would connect LP to C infinity or characteristic ratio. Okay? Now, what we need to do is to fill in the other half of the equation, right? That's another confusion, how we can fill in the other half. What we can do is multiply everything by 2. So 2 on the left side, 2 on the right side, to get everything.
The matrix.
Yeah, because you sort of fill in the other half of the matrix by multiply by 2. Because x and j is random, so you can do this type of thing. Straightforward? So that's where the 2LP is coming from. And on the right hand, you also use 2 multiplied by this. So this will be 1 over L, j equals to xn, Lx, Lj. So this part is relatively straightforward, right? Is it? Great. So the next, there's one more step we need to play. Then we are all set, okay? And that part is how we're gonna convert this to what we're gonna have in the next step is because this one is not the full matrix. It's not the end-to-end distance, right? End-to distance is where I just erased. Let me write here. So h squared would be equal to I equals 1 to n, j equals 1 to n, li dot lj. So that would be with the end-to-end distance.
So it's with the double sum now, are you taking into account maybe the other direction, the
right.
vertical direction? So that's why it's like you're finding the hypotenuse of sort of.
Yeah. So what you see is we only have adding one part of that. If you compare these two equations, what are we missing is the other half of all the sum of them together. In other words, you in that equation, what you will get is a full matrix where you got a 1, 1, 1, 2, etc. Right? Everything would add together. What we here is sort of missing the half of the matrix. Now, I think you guys I had enough equation. I'll just spell to the answer to you. A question again in the back?
I may have missed this, but are we applying like a model to this, like FRC or?
No, it's there's no model. It's a generalized. It definitely is not free joint model, because what we did at the beginning of this class is talk about free joint model. If it's FJC, the persistence length is just going to be L. It takes literally one bond to bend at 90 degrees, right? So what we do is taking account how does the chain angle is come into play. So you can sort of think about it's somewhere, it's applied to free rotation chain or hindered rotation chain. Both model would work out here. So you will get that's fine. So where this part coming from is now we have another transformation. We accounted all the n possibility, and we also divided by n here so that we normalized this n out. And some of you will ask me if it's L or 1 again. Okay?
So you're normalizing for the number of bonds.
Yeah, so yeah, n is basically, I added n times and I divided by n. So this n is cancels out this part. Because what this sum is, I sum n times of the same material, the same part here, and I divide by n. So in a net sum, I didn't lose anything or gain anything. So, in other words, so if you look at here, what I did is I can play one more trick. There's so many tricks. It's not a magician, but sort of like that. What I did is this, think about is one part. So I can multiply by n and divide by n. So this would be equals to, this part would be equals to 1, right? You didn't gain or lose anything. But now, if you multiply by n times the top part, this part, you can rewrite as sum of equal to 1 to n. J equals to 1 to n, because you added n times. And basically this part become this operation symbol.
How did the 2 get on the bottom of the equation?
How does the 2?
Because it was in the top of the equation to begin with.
Sorry, I missed your question.
So we multiplied 2 throughout the entire equation, and so how was it moved to the bottom
Oh.
of the original?
No, it's on the top.
Okay.
100%, it's on the top. Good catch. Okay, so now this is a second confusion that confuses you. Why there's a small tongue at the end of L. And this comes the fact that when we count the matrix, we will count twice of this diagonal term, and there's going to be a extra missing an L that we need to add here. Well, we count all these. But in the end, this L will not matter. Even with this with here or without here will not affect our final conclusion. And we will see why in a minute, okay? So this will be end-to-end distance, right? So we're going to still have 2 LP, going to equal to this part is going to be 2 divided by wait. This 2, let me check. This 2 should not be here. 2 and now. Sorry. This was not correct spelling right here. So the reason we did that matrix transformation multiplied by 2 on each side is where we can consider the full matrix. So that's where this is the confusing part for here is you will not have the 2 here, because now we use this to consider the full matrix. the 2 comes into here, right?
Okay.
2 comes into that half of the matrix. That is where the 2 is being consumed here. Because at the beginning, we only had the half of the diagonal matrix, whatever here. So that 2, if you multiply by this twice, you will have the full matrix, which comes into this equation. Okay. So there's no 2, but now this term is h squared, or CNL squared plus L. Or 2LP will be equals to C infinity L plus So what does this mean? We now get a direct connection between characteristic ratio and persistence length. And we can rewrite to be LP would be equals to, you can move the 2 here, so to infinity plus 1 L. And if C infinity is much larger than 1, LP would be, if this is much bigger than 1, this will be just a C infinity L, right? So that's the connection between persistence length and the characteristic ratio. So this is the length, but C is just a number, right? We talked about what the C would be. C infinity is somewhere between 3 to 9. We chatted about this ratio. So what persistence length would be is going to be about, up 1.2 up to 2.2 times of the bond for a typical FRC free rotation model or hindered rotation model. So this would be this value, okay? So this is the individual bond. So the physical meaning of this is roughly after 1.5 bond to average of 4 bond, your bond is bending 90 degrees. So it's relatively flexible chain. Let me give you some of the number. L, we know what's the bond for carbon-carbon bond. It's about 1.5 angstrom, right? So persistence length in this particular case is definitely less than 1 nanometer. So in other words, in a very common sort of relatively soft polymer, after 1 nanometer, your chain is already lose direction. It doesn't remember what's the direction for the several bonds before it. So it's relatively soft and coiled. In some more extreme cases where your chain can be relatively rigid is when your chain has C infinity or LP is much larger than 1 nanometer. I'll give you a few examples for the rigid rod-like polymer. So polyimide or any polymer has liquid crystalline property where they have a lot of double bond in the backbone direction. They can have persistence lengths up to hundreds nanometer or 1 micron. And if you remember the size of the chain is typically on the order of 50 to 100 nanometer. So these could be rod-like. And another rod-like extreme would be DNA molecular. DNA, they form double strands, and if you take a SEM or TM image on the bond, you will see this is relatively straight over long distance. So for these values we got, the key is you need to know this relationship. LP would be equals to half of the C infinity multiplied by L. We went a long way there But now let me put it here. Case 2 is, in a lot of cases, LP will be just equals to half of the characteristic ratio multiplied by L. Well, persistence length we talked about. We're going to talk about one more term today. It's used not a lot of time, but you absolutely have to know the name. It's called Coulomb length. Coulomb length is another polymer physics term that talks about chain rigidity. Basically, it's a sort of redundancy to what we talk about here. So Coulomb length, it was defined, it's going to be twice the persistence length. Or you can think about how much bond it takes for the chain to bend, not 90 degrees, but 180 degrees. So sort of for it to turn along. So Coulomb length. So you can think about bend 180 degree, okay? And Coulomb length written as LK will be equals to twice of LP. Or I guess you will see it's basically characteristic ratio multiplied by L. Right? And why bother to kind of, getting so many different terms, LP, LK, etc. And most of the time, you actually don't need to use both cases. You probably only need the one case. But there's one simplicity if you do polymer physics, which if you're a seriaticist, where you like, derive equations on the sheet, then this come into handy in terms of defining LK equals to C infinity L. Remember the first day we talked about H would be end-to-end distance will be C infinity and L square, and you can basically express it as two parts. You can express as this part multiplied by this part. And the beauty of this is now this is the contour length, LC, right? This is how long your fully extended chains are. And this you can just write as a Coulomb length. So you know how rigid your chain, you know how long it's fully extended. If you multiply two together, you will get end-to-end distance square. They were talking about a similar term. Okay? So I want to spend the last few minutes just to talk about one more items, do an introduction for the next lecture. It's called a worn-like chain. So still in these two cases where we still just chat about how does free rotation chain would actually affect these characteristic ratio and how does it link to persistence length. So if you read the textbooks, the next chapter will talk about some terms called a worn-like chain. So worn-like chain is it's a term describe how does a chain, if it's not in between, not rigid, not soft, it's sort of in between. There is some part of mathematics we simplified in the first two lectures cannot work in that scenario. So we need to come up a little bit different terms to describe that. And in the next class, we will talk about how does one-like chain can influence end-to-end distance and etc. And one-like chain is probably more critical for real-world application. As we talk about, not every polymer has all the backbone made of carbon-carbon bond. What if you have a benzene ring in the between? Then what we describe all here is not valid because, hey, these 3 bonds are tied together. If the one bond rotates, the next 3 bonds are going to rotate together with it. How do we handle this type of situation is what we're going to talk about in the next class. One-like chain model, it's a little bit more mathematics heavy. So based on the feedback I had this class, I think I will reduce that part. More talks about the first part of like 20-30 minutes in this class to explain how to interpret the one-like chain in the physical world meaning. Then we will jump a little bit, very little bit, mathematics. How does the one-like chain come into play? So with that, I think only going to cover half of the class. So the next half class, we will talk about radius of gyration. So you have heard many times about this term. And we're finally going to talk about this term. Because as I mentioned, this is not measurable in experimental scale. But RG, or radius of gyration, is measurable in terms of technique-wise. There's a scattering technique. You can directly measure what the RG will look like. And we'll just finish the one-like chain and talk about RG in the next class. Okay? With that, let's finish our class today. Then we will see everyone next week. Hey. I heard someone. Did someone ask? Hey?
What reading what chapter, what section should we have read for next time?
So if you follow me, I strictly follow the book.
Okay.
So right now I think I am at chapter 6.3. Next we will cover the rest of 6.3 and we will talk about 6.4.